Could everybody please find a seat so we could get started? Our guest speaker tonight is Dr. Douglas Falcon from the Los Alamos Scientific Laboratory in New Mexico. I'll let him describe some of his work to you. He is PhD in engineering from MIT in 1961. That's in nuclear engineering. In addition, he is a member of the board of both the American and the International Solar Energy sections of the International Solar Energy Society. He is chairman of the board of the newly formed Passive Solar Energy Group of ISIS, which is beginning to take a very new and exciting direction for solar energy. He is also chairman of the board of the New Mexico Solar Energy Association, which is a subgroup of ISIS, and is one of the largest in the country, something like 1,500 members. I would, without any further introduction, like to present Dr. Balcomb.
Thank you very much. I'm going to talk tonight about passive systems, but before I start that, I would like to describe briefly some of the activities of the laboratory where I am in charge of the solar program. It represents about 18 people working in a very large laboratory of the Department of Energy in Los Alamos, New Mexico, and it's basically a large nuclear science lab, and the solar energy activities represent a small part of the work there. We have chosen to concentrate our efforts on heating and cooling of buildings and have a relatively large activity in solar collectors, in passive systems, in a number of special projects, some of which I'll show you briefly. And we're also doing a lot of assisting of the people in Washington in the research and development branch on heating and cooling in the conduct of the national program, especially with respect to solar collectors and passive systems work. If I could have the lights down now, I will go through a few slides. The laboratory is located on a bench of the Jemez Mountains and is at an elevation of 7,200 feet at a latitude of 36 degrees north. So we have cold winters, about 6,500 degree days, and we have fairly sunny winters. So it's an ideal situation for solar heating, and it works very well there. The lab is principally involved in a large array of projects on nuclear weapons and nuclear science, but there are programs in geothermal energy, solar energy, fusion, both the magnetic and laser fusion concepts, as well as a number of other purely physics and chemistry-oriented researches. One of the first things we did in solar energy was, like most people, a solar collector. And we developed a structurally integrated solar collector unit, which means that the concept is that it's brought from the factory as a finished unit, ready to put up on the roof and play three roles: a solar collector, a structural element of the roof, and a watertight seal on the roof. It is built of steel and a expanded metal welded unit. It could be either in a single or double glaze configuration. This shows one before the glazing is put on. And here are some under test. We've built them with selective surfaces with 2 sheets of glass in one. A big array were set up, and this has gone on for a number of years. We're basically sort of out of the business of collector development, but now looking at specific things like selective surfaces and sealants and special glass and all of the special materials problems that go into making a good collector. But we did get 400 of these units built, a total of 8,000 square foot, and put on as a single planar array on a large building, which has just been finished in March and operated since that time. It's a 60,000 square foot building. It's a 3-story building, and the solar collector array is 8,000 square feet and forms the roof of the equipment room of the building. This is a walkway that goes into an adjacent administration building. If you make a cross-section through the building, there are the 3 floors, and the equipment room on the south side is covered over by this collector array. It's about the right space, and it lays into a 3-story building fairly well. You can look up inside from this visitor gallery and see the solar collector, see the bottom of them and the plumbing. The collectors are going on to a truss structure here, and there you see it during a March snowstorm last year. The analysis indicates that it will provide 96% of the heating energy required to run the HVAC system and 70% of the heat energy required to run the cooling system for this building. We have a lithium bromide absorption chiller, which is heat driven, and we also have an experimental unit, a Rankine cycle chiller, both about 100-ton capacity, and they both work very well. We've had a very successful summer's operation. Another project is an attempt to put cost-effective solar heating in the manufactured housing market. And here is the finished unit, which has been through a little over a year now. Here it was at Albuquerque Western Industries being constructed as an integral designed-in package with the solar collectors on the 60-degree south-facing slope and some windows left for visual access through the south side. It's an air heating collector system, and the storage in here, in order to save space, was water in 1-pint glass containers, and the air blows through them like it blows through a rock bed, and you get a higher heat capacity in the same space this way. We're also going to be trying phase change eutectic salts. We did try paraffin, and it didn't work out too well. We picked the wrong one, but we'll try some phase change salts this next winter. Another project is a air rock bed system on an Indian Pueblo near Los Alamos, and this is a single-story building with a second story in Pueblo style set back from it, and the collectors form the vertical section of this second story. And the performance is augmented by a Alzac aluminum reflector laid on the roof, which gives a performance which exceeds that of an optimally sloped collector by about 30%. And you get some benefits because this cuts off very effectively in the summer because of the geometry. We also use the Australian concept of a long horizontal flow collector. It's 66 feet long. It's basically one 440 square foot solar collector built in place. And it's just beginning operation now. So those are a few things that we're doing, and I'm going to spend the rest of the time talking about passive systems. Anytime I talk about this, people always wanted me to define it, so I'll just start off that way. I'll pick a simple definition to fit a simple concept. A passive solar heating or cooling system is one in which the thermal energy flow is by natural means. That is by radiation, by natural convection, or by conduction. And you don't have auxiliary mechanical motors or other equipment required to move the heat within the system. I have chosen to break down passive concepts into 5 different classifications. And the simplest and first of these is the direct gain approach, in which you simply use south-facing glass to let the sun shine in the building. And if you don't know it, you should know that a south-facing glass window is a very effective solar collector. The sun shines in and warms up the building. It's that simple. If it's double glazing, then it gains far more energy than it loses over the period of the heating season, if it's south-facing. That's true in every climate in the United States. There are some months, say, up along the Canadian border, where there are a couple of months where it might be a net energy loser, but over the period of the winter, it's a net energy gainer. And if you go to triple glazing or something like that, then there's no contest. You know that the cat likes to curl up on the floor there where the sun is or where the sun has just been, because it's a nice warm spot. Ray Bliss says, why not just let the winter sun shine in the windows? And why not indeed? It's a very effective mechanism for heating a building. There was a little study done by some people at the University of Illinois on a building, and they took a building which had an aspect ratio of 2:1, and it was lined up east-west, and compared two buildings, one with the glass equally distributed around the building on all sides, 144 square feet, and the other with 120 of those square feet of glass on the south side and a small amount on the north side and none on the east and west. And in the regular building, the contribution over the winter amounted to about 10.8 million BTUs over the heating season. In the building with the glass on the south side, it amounted to 14.8 million BTUs, quite a bit higher. In the first case, since it was a building built according to the ASHRAE 9075 standards, it was about 17% solar heated. It's hard to build a building that isn't that much solar heated. But the second one, which was much better insulated and had a number of special energy conservation features, was 35% solar heated, just passively. Now, I would call that a sun-tempered structure. It isn't enough to really be a passive solar structure. It's not over 50%. And at 35%, you don't have to worry particularly about extra mass in the building to accommodate the large solar gains. It just about takes care of the daytime heating most of the time. If you go over that, then you have to start worrying about some extra mass and very careful attention to temperature control and control of overheating. And that's the kind of building I'm going to be talking about. Windows can be used to create all sorts of effects. Here's a really rather nice one. Plays interesting light patterns on the floor. High-up clear-story windows can be used to let light and heat into the back part of a building. And you can use more and more. This is a house in Albuquerque with a south-facing sunroom, a brick floor to absorb and hold the heat. Here's David Wright's house in Santa Fe, New Mexico. He's gone all the way, and the entire south face of the building is fixed double glazing. There's very little glass on the other sides. It's an adobe or earth brick structure with the insulation on the outside. He calls it the sun scoop, and it's about 90% solar heated. He's got a small Franklin stove, and that's all his auxiliary. Here's a diagram of how that building works. It's really rather simple. It's designed so that on the winter solstice, the sun angle penetrates clear to the back of the building and heats up the floor and, by reflection, primarily the back wall. Whereas on the summer solstice, the sun angle is completely, never penetrates the south glass. And he does have some drop-down shutters inside for night insulation, but they're really not an essential feature in this particular climate. I think if you don't go away with anything else, you should have a good appreciation of where the sun is in the sky, because that is really critical. This diagram shows that, if you haven't studied it. The sun gets up in the winter about 30 degrees south of east, rises to a maximum elevation at a latitude of 36 degrees, it would be a little different here, of about 32 degrees, and sets to the south of west, also about 30 degrees. So it shines predominantly on the south side of the building. In the summer, it gets up north of east, goes almost due overhead, and sets to the north of west. So that it shines almost all morning long on the east side, hardly on the south at all, and can be controlled with a small overhang, and then all afternoon on the west side. And translated into energy onto the building, I've plotted this graph, again for a latitude of 36 degrees, from the ASHRAE tables. It shows that a east or west oriented face achieves about 2,000 BTU per clear day in the summer, which is the left edge of this graph, drops down to about 600 or 700 in the winter months, and goes back up again. Just exactly the opposite of what you want. Lots of summer heat, very little winter heat. Whereas on the south side, this curve, the one labeled south, has a dip in the summer and a maximum of about 1,500 BTU per clear day in the winter. And that's the same rough shape as the heating load, which is shown as the lowest stair-step curve here for Los Alamos. Again, a 6,500 degree day climate. And these are in the same units. So you can see that the south glass gains far more energy than it loses over any 24-hour period when there's a clear day. And even with average or cloudy days, it's usually a net winner. The north, of course, is a curve that peaks again in the summer and minimum in the winter, and the top, which is the red one, the horizontal face, has the same characteristics. So the south side is really the only readily usable one for passive solar heating. This is another building in Santa Fe, designed by David Wright, built by Karen Terry. It's an adobe building with a lot of south glass, and it's bermed up heavily on the north. If you aren't careful approaching this from the north, you step on the skylights. It's really dug in, which gives it a lot of a low loss because of the moderate earth temperatures and a large extra mass. Very delightful building. Inside, it's light and cheery because of a lot of sun coming in through the south side. Does not overheat at all in the summer. It's just been occupied beginning of summer. I expect it to be getting 75% or more of its heat from the sun. It's an adobe structure with the insulation on the outside. In Liverpool, England, the Wallasey School is also a solar heated structure. I think it's about the oldest and largest modern day passive structure. It was built in 1962, designed by the architect A.E. Morgan, who unfortunately died the year after it was completed. But it was a very forward-looking design, and he built a concrete structure 7 to 10 inches thick, and then insulated it on the outside with 7 inches or 5 inches of expanded polystyrene. And the entire south facade, which is about 27 feet high and 230 feet long, is double glass, fixed. Almost all of it's fixed. The outside layer is clear glass. The inside layer is a figured glass, they call it, which refracts the light to more uniformly illuminate the inside of the building. I'm inside now. I was taking this picture with my back to the wall inside the assembly room, and you can see that on a day when it was raining outside, which is par for the course in Liverpool, England, there's a rather nice lighting inside, and they might want some lights over on this side to balance the lighting. But there's a natural control system operative here. If there isn't much sun, they need more light, and so the teachers turn on the lights, and that provides the heat that the sun does not. If there's plenty of sun, they don't need any more heat, and they don't need any more light either. This shows the figured glass, which breaks up the image and keeps the school children from being distracted by what's going on the playing field outside, and also a steam heating radiator down here near Morris Davis's feet, which was installed because you've got to have an auxiliary to satisfy the Board of Regents. And that was installed in 1962. It's been turned on once for a 1-month period since then when they had an electrical failure for a month. They had to turn that on to maintain temperatures because they didn't have the lights, and so that didn't provide the heat. Morris Davis has carefully monitored the performance of this building. He's from the University of Liverpool, and he calculates that the building is about 50% solar heated, the other 50% being supplied by the students and by the lights at 53 degrees north latitude. Here's another structure. This is by the architects Taos, Bill Mingenbach and Company in Taos, New Mexico. It's a roof aperture design in which he's used 3 clear stories to let the light in through the roof of the building onto mass in 55-gallon drums stored high up and out of the way so it doesn't use up usable floor space. The building is 2x6 construction frame with full insulation, and it has a traum wall on the south side as well. Up on the roof, he's used a reflective aluminum roofing to get a little more augmentation, get more sun through the windows, and you can see that it's working by the play of light up on this board up on top. The second category of passive system is a thermal storage wall, in which instead of placing the mass back inside the building, you move it out and place it immediately behind the double glass. That has 2 advantages. It reduces the glare and the light in the room, which might fade carpets or be too intense. It also reduces the temperature fluctuations that are associated with the direct gain approach. The classic of this type was popularized by Felix Traum in the Pyrenees in southern France, and this building, built in cooperation with the architect Jacques Michel. It's a simple rectangular structure with a 2-foot thick concrete wall located immediately behind double glass, poured concrete wall. And it's otherwise a masonry building, and they've measured its performance in a cold, high altitude but sunny climate, and it's 70% solar heated with a electrical backup that's set at 70 degrees Fahrenheit. The heat is absorbed on the outside surface of the concrete and heats up that surface to temperatures of about 140 degrees Fahrenheit peak during the day. That heat diffuses through the concrete by thermal conduction and is then convected and re-radiated to the room at the inside surface. There is also a convective loop, a thermocirculation path shown by these arrows, by which they get some daytime direct heating using this outside passageway as an air heater, which naturally convects in a loop around. It's interesting to note that buildings of this type do not stratify. They have good mixed air inside because they're heated from the side, and so there's a natural convective loop within the structure, whether or not the thermocirculation path is there. And it's very effective at mixing up the air. There is a picture that I took of the lower vent inside, which lets the air into the outside passage. And at the top on the right there is a board up toward the roof, which covers up the upper vent, which is otherwise rather unattractive, and just for visual effect there. But you notice that the inside of the wall is white. No reason that it need not be, because white paint has, in the infrared, as high an emittance as black paint would have, and so the re-radiation which takes place is just as effective with a white wall as it would be with a black one. And of course, it's a much nicer room with the light color. In Princeton, New Jersey, architect Doug Kelbaugh built this house for himself, and he's been through 2 winters now. It's a frame structure, except for the south wall, which is poured concrete. Now, he wanted to be able to see out on the south side, so he just naturally left windows through there, and that's fine. He put single glazing in those windows, and then on the outside, double glazed the entire outside surface. He left a greenhouse over 1/4 of the outside because he wanted to grow some plants. And he gets a very nice environment in there. This is Doug, and it's a very relatively stable environment. You can see out into the greenhouse here, and having a greenhouse immediately adjacent to the kitchen there is very pleasant. This shows that there are 2 convective loops in this 2-story house, one upstairs and one downstairs, and they're fairly independent. He does have a simple way of preventing night reverse thermocirculation of air around through the vents, and that's shown on the right. That's the 3-cent solution there to that problem, a piece of lightweight film plastic and a wire cover to prevent it being sucked in. It closes automatically at night. And if you don't have that, you're better off not to have the thermocirculation path at all, because it'll lose more heat at night than it provides during the day. We're instrumenting this building at Los Alamos. We've got a recorder in it and a bunch of thermocouples. And here's some data taken last March. The lowest curve on here, this isn't showing up very well, its batteries are going out. The lowest curve is the ambient temperature, sitting down around a 35-degree average, and the upper curves are taken inside the building. The top one that is green is the outside wall surface temperature, and this is in March, and the peaks aren't very high, 105 degrees or so. The red curve is the air in the lower room, and the black curve is the air in the upper room. This is over about a 2-day period. And you can see that without any auxiliary heating at all during this period, the sun is holding the room temperature up at an average of about 65 degrees. The right-hand series of graphs shows a number of measurements made at different depths within the concrete wall. The top one is at the outside surface, the next one at 1 inch in, 4 inches in, 8 inches in, and so forth, clear to the inside surface. So the high peaks on the outside just aren't seen on the inside. You have a relatively mild temperature variation. And there's a big time delay, about 10 hours, between the outside peak and the inside peak. So the building is heated by the wall as a large radiant panel in the evening when you really want it. Another trom wall, as it's called, structure is that of Bruce Hunn in Los Alamos, a co-worker of mine. And he built a 2-story frame house with a wall which was built of a hollow concrete block, and as he laid the wall up, he filled the cores of the concrete to make an effective 1-foot thick masonry wall, 12 feet high, 27 feet tall. On the right there, you can see it before the glazing was put on and before the wall was stained, and it shows how it's built a little better. The vents are just for a summer circulation. They're not used in the winter, the holes there. And he has some direct gain through the windows on the side. He also has a nice view to the south, so that helps. This is a hybrid design. He has a rock bed underneath the floor and takes warm air out of this space between the glazing and the wall and puts it in the rock bed with the assistance of a fan so that he can heat the rest of the house, the wing on your left, with that hot air. The building is about 60% solar heated. Here are some data taken about where the workman's level is there last January. This is during a period when there was no auxiliary required. The average outside temperature was about 20 degrees Fahrenheit, as shown by the black lower curve marked ambient, and the solar radiation is the lower red curve, and the other four upper traces are measurements on the outside surface of the masonry wall, 2 inches in, halfway through, and on the inside surface, showing the same sort of a smoothing and delaying effect of the diffusion of heat through the wall. Another way of putting thermal storage in a building is to use water. And Steve Baer's famous house in Albuquerque utilized 55-gallon drums filled with water as the cost-effective approach. He has these stacked up in an array behind single glazing and uses a folding door arrangement. On the left, you can see the doors are folded down. They hinge along the lower edge. And on the right, how they lift up, and there's one just barely cracked open to provide night insulation to seal the heat that you've gotten during the day into the building. He also gets about 15% augmentation of the performance due to the reflection of sun off this shiny surface here. A very effective approach, and he has a boat winch inside and gets a little extra exercise by cranking that up every night and down every day. Inside the building, on the left, during the day, you get a nice sort of star pattern diffusion of sun through there, which lights the interior, and at night with the doors up, shown on the right there. This is another building which combines the direct gain and thermal storage wall approaches. It's the Dove Publications building at the Benedictine Monastery in Pecos, New Mexico, designed by Zomeworks. It's a 7,000 square foot building long along the east-west axis with all available south glazing they could get. The front part of the building is office space, and the back part of the building is a warehouse. Here's a crude plan on your left and section on your right of the building that I sketched. The warehouse is in the back part and is about 2/3 of the volume of the building, and the office is out in front. The back part is heated by direct gain through upper clear-story windows. The front part I'll go into in more detail in a moment. In the back part you can see that stripe of sun shining into the warehouse space. They store books in there, pamphlets that they're going to sell, and that is the thermal storage in the building. Here are some data taken by Los Alamos during last winter. The warehouse space, which has no auxiliary heating at all, averaging about 48 degrees Fahrenheit. The minimum temperature in the warehouse last winter was 43 degrees. The minimum temperature outside was 14 below. The front room runs about 10 degrees or 15 degrees warmer than the back room because it has more gain and more thermal storage. The thermal storage there is, naturally, since Steve Baer had something to do with this, in 55-gallon drums. Here you can see that they're stacked too high. There's 138 drums running clear across the south face behind double glazing. And he has a reflective fold-down door, which wasn't on at this time. Up above, there's direct gain into the room. Those drums are inside of a space which covers over with a working counter inside, so there's really no effective space lost in the building to thermal storage. And a natural convective loop goes down through radiators at the floor level and back out the radiators here at the about waist high or a little below. And the people in the building can control their own environment by opening or closing those radiators. They do have radiant electric panels on the side. In this 7,000 square foot building, their total electric heating bill for last winter was $80. They turned it on 2 or 3 times when it was cloudy for several days at a period. The next approach is the solar greenhouse, which is one of my favorites, in which you get a usable space, a direct gain space on the left shown here, and the living space, which is much more carefully controlled on the right. And in between, there is a mass wall which functions like a Tron wall to collect the heat and diffuse it through. Bill Yonda, my neighbor in Nambe, has sort of popularized the solar greenhouse and written a nice book about it. He builds them as retrofit structures on the south side of buildings, and there must be 100 of them in New Mexico by now. There's one of the early ones. Total materials cost for the 2x4s and Alaska Light is about $3 per square foot for the greenhouse space, and it needs no auxiliary heating at all. It never freezes in the high valleys of northern New Mexico, provides food and heat to the building. If you don't have a masonry wall behind it, you need to add water in the form of drums full of water or some other thermal storage in there, pardon me, in order to reduce the temperature fluctuations and hold daytime heat over to the night. Here's another solar greenhouse at the Ghost Ranch project where they have dug it down a bit on the outside, which is a good idea. Again, it's double glazed with a fiberglass acrylic, which is a good solution for a greenhouse. Here's another one where they used a flexible plastic as the glazing, 2 sheets of it sealed all around the edges, inflated with a small 25-watt fan, which provides a very rigid but demountable structure. You can take it off in the summer. This is on Hal Miguel's house in Tusuki, and his only problem is that the cats like to climb up the outside of that plastic, and that creates a little bit of difficulty. But it provides, this is taken in the middle of the winter in a climate that's at least as cold as yours. I built this on my previous house in Los Alamos just to show you can vary the geometry quite a bit and get away with it. Use some roof aperture there, a lot of south-facing glass in basically a frame structure, and managed to get through the last winter without any auxiliary heating after I got a rock bed going, and I'll show you that a bit later. This is my current house. I moved to in Santa Fe. It was designed and built by Wayne and Susan Nichols. The architect was Bill Lumpkins in Santa Fe. The building is an L-shaped plan with a large 2-story south greenhouse. And I apologize for this picture because you probably can't see it very well. I've got a better one in the works. But you can see the L-shaped plan with the living space behind and the greenhouse in the triangular space out front. The wall between the house and the greenhouse is a 14-inch thick adobe wall, which is the main thermal storage in the building. The back wall is not adobe, it's frame stucco, and it is built with 2x8s, fully insulated, about R30, with 5 inches of polystyrene on the roof. You see that the building is sort of almost an approximation of a dome. It has a minimum surface area to volume ratio, and the quadrant that faces south is an aperture to let the sun into the building. All that south glass is sealed double glass units, clear glass units. In the greenhouse, you can see that in the winter the sun would shine through there onto that mass wall and heat it up. There's a circular staircase to get you up from the lower level to the balcony, which serves as the access to the upper bedrooms. Inside the back portions of the house, you have very little glare. You can control the amount of light there by the amount of glass you put in, and it's very comfortable space. The maximum temperature in the back rooms this summer was 76 degrees. It's very protected from the high temperatures of the greenhouse, which got up into the high 90s. But there's a big vent at the top of the greenhouse which allows the whole room to chimney through and prevents overheating of the greenhouse when that window is open. A very elegant design, but a very simple one. It has an active element. There's a fan which pulls air out of the top of the greenhouse and runs it through an underfloor rock bed to store a little bit more of that warm air in the greenhouse within the building. And the rock bed is a total of 50 tons of rock underneath about half of the floor in the back portion of the building. So the heat diffuses up through that concrete floor, maximum temperatures of about 80 degrees, and warms your feet. As Wayne says, a warm floor on a cold winter night is like a cuddly puppy. Around behind, carefully hidden from view, I've got a couple of active water heating solar collectors which provide my domestic hot water, and they work very well. I think that's a fine system. And on the right, you can see that most of the north aspect of the building is very little bit of window in order to minimize the losses. The next approach is the roof pond, in which the mass is put on the roof of the building. This is a design which is certainly most suitable for use in a arid climate. I won't go into it. It's been popularized by Harold Hay. It's the Therm System, and probably not altogether suitable for your climate. It's a good passive cooling system and only a moderate passive heating system. There's the Atascadero house that he built, flat-roofed house with sliding panels that slide back and forth on the roof to allow night sky radiation in the night and in the summer and prevent gain in the day. They also are operated in reverse during the winter to provide gain during the day and seal the heat in at night. Another roof aperture approach, or roof pond system, is being built by Los Alamos in a second mobile modular house. This is a factory-built house and has 4 sawtooth roof apertures to allow the sun to shine in onto bags of water, which are in the steel roof truss space overhead, and the heat then radiates down into the building. The design has a small hinged door which allows you to drop an insulating panel there at night and seal the heat in and provide some degree of control. If you're getting too much gain, you can shut it out. You can operate it in reverse in the summer, although it is not a good cooling system because it's fairly well sealed up. The next approach is a convective loop, where you use an ordinary solar collector and an ordinary storage, but you locate the collector below the thermal storage so that the working fluid, by natural convection, will carry the heat from the collector to the thermal storage, deposit its heat, and return again. It's a passive and automatic system. It cuts off automatically at night. Somebody was going to get me some water, and I'm going to need it before long. Here's a couple of classic thermosiphon water heaters. The one on the left is a Zomeworks design, which is being marketed for about $800. Double-jacketed tank with the non-freezing fluid in the outside jacket, which convects around the collectors. The inside tank is the water. The one on the right doesn't have that double loop system because it's in Florida, where it doesn't freeze. And they use these on the beaches. In Florida, you can walk down the beach and have a nice warm shower, courtesy of the sun. Another convective loop system utilizes air. This is the house of Paul Davis in Albuquerque. It was also designed by Steve Baer. The collector is the lowest element in the building, and there's a metal lath type of collector. The air goes through that, is heated up, and deposits its heat in a rock bed located somewhat above the collector, and then returns by natural convection. Heat is then distributed to the house by another natural convection loop. And when you lay this out this way, it works quite well. At Los Alamos, we have, as part of our program, the monitoring of several buildings. I've shown you some data. Thank you, Stan. I showed you some data that we took on some of these buildings. This winter, we have 15 different buildings of all different types on which we are taking records. In addition, we've built 14 small passive test rooms at Los Alamos where we're trying out all sorts of different concepts. There's a plan view on your right of a couple of those test rooms with thermal storage walls installed, one with a 16-inch concrete trom wall, and the right-hand side has an equivalent thermal storage mass in water located in 12-inch diameter tubes sitting on the floor. Here are some data taken last January on those test rooms. The outside ambient temperature over this 2-day period was about 20 degrees Fahrenheit. The inside average temperature in both rooms was about 90 degrees Fahrenheit. No extra heating at all. Number 1 there on the left-hand curve is a trace at the bottom of the water tube. 2 is halfway up and 3 is at the top, and 4 is a room temperature measurement, a globe temperature. On the right, in the concrete wall side, the peak curve there is on the outside surface, peaks of around 160 Fahrenheit. That's 5. 6 is halfway through the wall, and 7 is on the inside surface. And the lower pair are temperatures taken in the room. So they're performing quite equivalently. And it's been interesting to find out that a concrete wall can perform about the same as a water wall. They have somewhat different characteristics, but to first order they're the same if the heat capacity is the same. We have devised mathematical simulation models, mathematical representations of these buildings, and we can schematically show them as thermal networks, as shown on the left, in which different points in the system are shown interconnected by thermal conductances from point to point, shown there by the resistance symbol. And then we calculate this hour by hour using the observed values of ambient temperature and solar radiation. On the bottom is a similar representation of the concrete wall, which is a bit more complex. And the point of this is to indicate that with these kinds of relatively straightforward and simple mathematical representations in a computer model, we can predict after the fact the temperatures within either one of these rooms at any point, generally within about 2 degrees Fahrenheit. And at the most, we're out by about 8 degrees. On the right, you see some of the comparisons. The solid line in each case is the calculated temperature, and the little X's in each case are the measurements. The bottom is the ambient temperature, which is input. The top curve is the water temperature. The next one down is the room temperature in that side. The next one is the outside wall surface temperature on the concrete wall side, and the room temperature there. So that we have a tool, a mathematical tool for analyzing and understanding these, a mathematical tool that we have validated for these relatively simple geometries. And so we can then say, what if? What if we put auxiliary heat in here and set up a set of conditions like shown on the left, which I call a reference case. An 18-inch masonry concrete wall with thermal conductivity and heat capacity equivalent to that of dense concrete, some thermocirculation vents which are allowed to run only during the day, a load which is shown, say, on this right-hand sketch by that little resistance on the right. This isn't working. And that's a representation of the total conduction from the room to the outside, except for the wall, including infiltration effects. And then we provide auxiliary energy to maintain a temperature band between 65 and 75 Fahrenheit. Calculate hour by hour for a given series of weather data, solar radiation and ambient temperature taken over a year period, and see what happens. Here are some results for a few locations where we had hourly weather data and hourly solar radiation data. The cities are shown on the left, the heating degree days, the next column, the annual fraction of the heat that was required by the building the percent of solar heating, that is. The next and the final one on the right is the total number of BTU per year per square foot of south wall that was provided net to the room by the tram wall. And you can see that we're getting 30 to 60 or 70,000 BTU per square foot per year out of that wall in most places. The worst one on there is Hamburg, Germany, where it's really awfully foggy in the winter, and it just doesn't work very well. But further north in Denmark, it's interesting that it works much better. Here are a few more cities. On the left, some really cold places. The closest one to you is probably Madison, Wisconsin, which had a 42% solar heating fraction. And some Winnipeg and Edmonton, even there we're getting some net solar heating out of the south wall. And a few warm places over there on the right, where of course it works exceedingly well. One should, in the very cold climates, I would say, provide either triple glazing or some means of nighttime insulation, of double glazing. The other sort of what-if game we can play is, what if the wall were 16 inches thick instead of 18 or 2 feet thick? What if we used the wall without the vents, and what if we made it of water? We've run hundreds and hundreds of cases. On the left, you see some of the results for Madison, Wisconsin. Notice that the scale here is compressed from 30 to 50%. So they're all competitive performers. And the parameter I'm plotting there is the thermal storage, which for the concrete walls is about the thickness in centimeters. The solid wall has an optimum thickness of about 30 centimeters, which is a foot. The tram wall, a better performer, has an optimum thickness of about 18 inches, 45 centimeters. And of course, the water wall just gets better and better as you make it heavier and heavier. On the right's another parameter study where I show the annual solar heating fraction. This happens on the right to be for Los Alamos. This is a function of storage heat capacity for a water wall. And the four curves there indicate the influence of using double glass, which is the solid red curve, or single glass, which is the solid green curve. And you can see that single glazing, even in Los Alamos, doesn't work well at all. It just loses too much heat at night. And the dotted curves are the ones where we put in place at night an R10 insulation, a folding door, a bead wall, anything that would effectively insulate it at night. And it improves the performance of the single glazing tremendously. That's like Steve Baer's folding door. With double glazing, it's even better yet. And say for 70% solar heating, you can get by with half of the glazed area if you have night insulation. Of course, night insulation is a hassle, and it's expensive, and you have to trade off whether you think it's worth it. I'm going to go through a few techniques now in my closing comments, just specialized topics that get brought up when you talk about passive solar heating. One of them is how to get mass in a building. You need mass because these buildings have so much energy coming in during the day, they would overheat. They'd go over 100 degrees easily, even on a cold day, if you didn't have mass in the building to soak that up and moderate the temperature. And it carries that heat over into the night. You need about 30 pounds of water at least, or 150 pounds of masonry at least per square foot of south-facing glass in the building as a sort of rule of thumb. And that's mass in the direct sun. If it's not in the direct sun, you need about 4 times as much. That's a lot of mass. And here's one way of doing it. Build a masonry wall and then insulate it on the outside. This happens to be adobe, which is a building material often used in New Mexico, stuck on the outside of the building, and then stuccoed on the outside of that later on. works rather well, and you can see the finished building on the right. That's Karen Terry's original house designed by David Wright. Another way is to use water in drums. On the left, in Doug Kelbaugh's greenhouse, are a couple of 55-gallon drums doubling as planting benches for the plants, and they're painted black. Those drums vary about 10 degrees over the course of a day, which means they're storing and giving up an awful lot of heat every day. That's very cost-effective if you do the economics. On the right is a drum being buried in a bunco in Al Newton's house, designed by David Wright. I don't know that that's awfully effective because thermally it's awfully remote from the room and probably doesn't interact much on a daily basis, but might on a weekly basis somewhat more. That was covered over afterwards, of course, with more mud to form a bench to sit on. You can use water in various forms. On the right-hand side, someone's building up a drum wall, a water wall slowly. They're drinking themselves into thermal storage. It's a nice way to go. On the left are some tubes made by the Calwall Corporation. They're fiberglass tubes wrapped around and black on the outside, filled with water to get a lot of thermal storage mass. Could be done. You could get some nice architectural treatments with various combinations. In a hybrid scheme, you can use rocks and blow air through the rocks. Rocks don't work very well if you don't blow the air through them, and you need a fan for that, of course. This is my greenhouse in Los Alamos. One day the dump truck left me 10.5 tons of rock on the front lawn, and the teenagers there helped me out. I've got an exercise for the students here. If 4 teenagers at $1.50 an hour take 3.5 hours to move 10.5 tons of rock, how much is that per ton? I'll give you the answer. It's about $2 a ton. Not too bad. What I did then was use a fan that blew 1,000 CFM of air through these rocks, and I just turned the fan on during the day, which warmed the rocks up about 8 or 10 degrees from the warm greenhouse air. And then at night, I had a thermostat on the fan, and if the temperature in the greenhouse dropped to 50, I turned the fan back on again and retrieved that heat from the rock bed. I needed auxiliary heating in this room until I got the rock bed going. After that, I needed no auxiliary heat. I computed the net effective COP, or coefficient of performance, the heat I got per unit of electricity I had to spend, and it was 12. Pretty effective use of electrical energy, say, compared to electrical resistance heating. Another technique is movable insulation. Here's the Masterson studio in La Cienega, New Mexico, a very simple building, and he's got some sliding doors, rather attractively built, insulation on the inside, open on the left, closed on the right. A simple scheme of getting movable insulation. Another technique is to have a folding door inside. This is one in Albuquerque, simply a panel controlled by a couple of ropes that swings back and forth. It can be, as all of these can be, used in one mode in the winter to try and trap heat, and in another mode in the summer to try and prevent heating during the day and let it out at night. Another scheme is the skylid, invented by the folks at Zoneworks. Up on the top, you see that during the day, these louvers in the roof